Okay, welcome everybody. Thank you for attending today's webinar on determining economic life cycle in CAM. My name is Rick. I will be acting as moderator for today's presentation. We are going to go ahead and get started in just a second, and right off the top, I would like to first say we are very excited to have Marc Knight as our presenter today. Some of you may have recall having attended the webinar he hosted about 2 years ago on a similar topic, how to manage the life cycle cost of your fleet. And some of Marc's other key areas of expertise include replacement planning and funding, procurement, as well as outsourcing and operations assessments. So we do feel very confident all of you will enjoy some of the features, models, and analysis tools to determine economic life cycles in CAM, and Marc will be demonstrating all these today for our attendees. Just to give everybody a quick heads up before we start, the microphones have been muted, so if any of you do have any questions at any time during the presentation, all are encouraged to use the WebEx chat tool. All of you should see a chat icon located on your screen, and this will act as an instant messaging tool. So please feel free to use the WebEx chat tool to enter any questions during the presentation, and just be sure to address them to host, and I'll be more than happy to field them and then relay them to Marc at the conclusion of his presentation for a brief Q&A session. All right, Marc, so with that said, I do think we're ready to get started here. Looks like we can see your desktop, so you can take it away whenever you're ready.
All right, well, good afternoon, good morning, and good evening. We had several hundred people register for this, including a couple as far away as Australia, where it's 5 a.m., and a couple of our customers from the UK, where it's pub time. So welcome, everybody, to today's webinar. I'm happy to be here and give you an overview and understanding of life cycle cost analysis and how that plays a role in effective fleet management, but also talk about how we have implemented life cycle cost analysis in our capital asset management tool. CAM is a new initiative that we've started several years ago, and we actually have been in deployment for about a year, and I'm going to talk about how we've deployed the capabilities to manage the life cycle in that application. So first I want to start with just a general overview of life cycle cost analysis. Just to give everyone a little bit of background on what we are talking about and the functionalities and capabilities of that tool. To be a good asset manager, there's a couple of objectives that you really have in your organization. One is to overall minimize the total cost of ownership. We want to replace vehicles at an optimal time when the cost to own and operate those vehicles is at their lowest. There is a methodology out there for doing this. It looks at total ownership and total operating costs, combines those, and tries to find an optimal point. There's also the ability to manage scarce resources. Capital is something we never have enough of. We always have a limited amount. Those that have it, dole it out very stingily, and when we get it, we need to know what to do with it the best that we can. So one of the things we want to consider is the overall cost of an asset. You have the initial cost. Two assets may be similar in value, or one asset may be more, cost more to obtain. But when we combine in maintenance costs and operating costs, we may find that an asset that is less expensive to purchase might be more expensive to own and operate in the long run. And so life cycle cost analysis gives us a tool to help us manage those decisions. The other thing we want to do is be able to implement effective management strategies. There is a relationship between capital spending and maintenance spending, but it's not a one-for-one. Many decision makers think that if they, don't give you $1 million in capital, that they'll save $1 million in maintenance. Well, that's not necessarily the case, as we all know. There's upfront costs and then there's ongoing operating costs. But we need to be able to understand what those decisions are and what those impacts are and what the cost is over the long run. Additionally, we want to be able to make good repair versus replace decisions. Should I invest in something today, or am I better off buying a new asset instead? And so part of what life cycle costs can do is help us to understand what those decisions are. So if we look at the stages of an asset through its life, we have the procurement process. And in the procurement process, we have the upfront investment And then we have all the acquisition and installation and upfitting costs that go along with that. Once that asset, is in the fleet or, is active, we're in that operation and maintenance stage where we have a number of costs. And this is typically, these are costs that are captured in your fleet management system, FA, M5, or another system that you may operate. It's, your ongoing operating costs, labor and parts, whether they be internal or commercial, energy or fuel costs, the cost of downtime, any costs I might have to go through during the life to renew or rehab the asset, and then there's the ongoing capital depreciation expense. And then at the end of the process, we get down to the replacement and disposal. And there's decisions here about how do we best remarket the asset. Do I sell it? Do I sell it to employees? Do I auction it? Do I donate it? Do I crush it? There's all decisions that we can make at the end of the life that affect the total cost of ownership. So what life cycle cost analysis is a tool to help us really look at what are our cost-effective options. And when we look at different decisions, we can take that cost analysis of each of those decisions and compare them to one another to see which might be the best. And typically what we're looking at is the total cost of ownership. In this case, we're dealing with capital and operating expenses. And we want to measure the long-term economic viability of the asset over different lifespans. Whether I keep it 5 years or 10 years or 15 years, what is the cost of each of those lifespans and which is the most cost-effective? The other thing the life cycle cost analysis does is helps us understand the impact of age and utilization. We all know that as assets get older, they require more maintenance, utilization tends to fall off, everyone wants to drive the new one up front. All of these things can be illustrated through the impacts of the cost in each year of the operation. And by taking these tools, there's a couple of different decisions we can make as asset managers to decide when to replace things, and then also what to buy. Which specifications have the better life cycle costs, which are going to give me the bigger return on my overall investment. And then also how to maintain and implement maintenance strategies. And so if we go back and look at those three goals that we have as managing our assets, with a life cycle cost analysis, when it comes time to minimizing total cost of ownership, I have the ability to calculate my replacement guidelines. I can use the tool to determine when is the optimal replacement for a specific type of unit. And then with that, I can take that replacement cycle and apply it to my fleet and come up with a forecast of replacement requirements. And when it comes to managing resources, again, I can use life cycle cost analysis to make a buy decision, which is the better asset to buy. I can also look at two different assets that may need to be replaced and evaluate those independently of each other to see which might be the better one to choose when funding is scarce. Do I go ahead and replace a dump truck that costs $50,000 a year to maintain, or 10 sedans that might cost $2,000 a year to maintain? They might cost the same up front, but maybe I'm going to save some money on the back end with maintenance. The other thing I can do is I can use this data also to set lease rates and rental rates. I can look at what my ongoing expected costs are going to be in the category in each year and then use that to build into a potential lease or rental rate. When I'm dealing with maintenance strategies, again, repair versus replace, which is a better investment, the new engine or a new truck? When I'm looking at maintenance strategies, do I want to outsource? Do I want to go with a full warranty? Do I want to buy extended warranties? All of those decisions can be supported with a life cycle cost analysis. And then finally, we want to look at forecasting our maintenance requirements. What are our staffing needs? Based on the age and distribution of my fleet, can I estimate what my maintenance hours are going to be and then determine what my staffing requirements might need to be for an in-house operation? And then also, what are my budgets? What am I going to need to spend given the age and distribution of my assets? So when we talk about life cycle costs, we're really dealing with two types of costs. There's cost of ownership and cost of operation. Ownership is going to be all the capital up front. There's going to be my procurement costs. There's all the invoice, delivery, everything that's added to that invoice above and beyond just the base cost of the asset. Maybe I did purchase an extended warranty and I'm going to capitalize that. There might be some services, some training, and some other things that I've capitalized along the way. I'm also going to, so that's going to give you my upfront total cost. Well, that total cost gets expressed in depreciation. that becomes the use of that asset over time and the decreased value of that asset based relative to what I can sell it for at different stages in its life. There's also interest and inflation that needs to be factored into this, and ultimately then at the end there are some disposal costs. There's some costs to prep the vehicle, get it transported to the disposal site, commissions and other things that go in there that are part of that. And those can vary from asset to asset depending on the type that they are and how I do dispose of things. When we look at operations, we're looking at really the ongoing costs that affect the life of the asset. So our basic operations, fuel, PMs, oil, things that go into, that are consumed by the asset on a regular basis. We look at both scheduled and unscheduled maintenance, but we do exclude operator damage and crash costs because those really aren't a factor, or if they never occurred, we never have those costs. So we don't want to include them in a life cycle analysis to determine optimal replacement. Downtime, though, is something that we want to factor in, and actually becomes an interesting way to influence the life cycle cost analysis, because over time vehicles are out more frequently and they're down longer, and there is a cost to that, and we want to be able to factor that in. Cost of obsolescence that we can directly attribute to the vehicle, we want to include. Indirect things we exclude, and I'll talk about that more in a minute. Operator training up front, maybe something we include, and then a cost of inventory, overhead, those type of things. Typically those are expressed in markups to your parts operation, that it becomes part of the base cost of the vehicle. So those direct shop overheads typically get included through our markups and charges. But again, I talked about some things that are excluded, and typically what we don't include are the non-target costs, costs that really could be avoided through good operation, good practice. They're not something related to the form and function of the vehicle and the operation of the vehicle. So typically accidents and physical damage are excluded, theft, things that are outside of our control, any modifications that aren't capitalized. They may be, if they are ongoing, something you do normally. You don't capitalize it, but you want to treat it as a maintenance expense. That might be incurred, but if it's some minor things, we typically don't direct those. If they're considered non-target, they're optional type modifications. And then accessories, things that get added outside. If I capitalize them, they can be included. Some people will include these. It's kind of a by choice, but generally they're not. And then we look at operating costs that really aren't life-altering, things like license and permits and tolls and car washes. Some of those things are by choice. Some of those things are regulatory. They don't necessarily have an impact. I have to pay them for everything, so they're usually excluded from the analysis. And then typically one-time costs that I might have that aren't really due to the asset's failure or the asset's age or use, those type of miscellaneous costs we tend to ignore. And then indirect external costs, they're typically for a life cycle cost analysis, we don't have a way to include those. They might be added as part of a rational decision analysis afterwards, where life cycle is given part of the weight of that decision matrix, and these items are factored into that decision making, but they're not directly attributed to the life of the asset. So I'm going to talk now, laid out generally what life cycle cost is, and then talk about the methodology that we built CAM around, which is the mean equivalent annual cost method. This is a pretty commonly adopted methodology in the fleet industry. It actually dates back, my first reference I was able to come across was a 1972 pamphlet from the APWA that laid out this methodology. I've used it for over 25 years in the fleet industry as a consultant. It's also referenced in different papers throughout different organizations and in the industry. So it's something that you can easily find. There's Wikipedia and everything else out there on the method. So this is a pretty standard formulation for calculating life cycles. And really what it does is it looks at the total mean cost between varying life cycles. So it compares the cost for 1 year through cost for 20 years, however far out you want to do your analysis. It looks at each of those costs and then helps you determine the optimal replacement point by finding the year or the lifespan that has the least total cost in that particular point in time. And you can also use this methodology and the costs that are generated out of it to do some additional analysis, and I'll talk about how we're going to do that. Key to this idea is the idea of an equivalent annual cost, and this is an annuity that looks at the cost over a particular lifespan. And the case is, for our analysis, again, we're looking at cost of maintenance, downtime, and fuel. Those are things that we can collect and attribute to various age and utilization points in an asset's life. We can aggregate those over time. And then cost of ownership, which in this case is represented through depreciation. What is the lost capital value in each year of the life, and what is the remaining value, and then factoring that into the analysis. This formula here represents the mean equivalent annual cost calculation, where essentially we're taking purchase price less the resale value plus the sum of our operating costs over time, and then applying an equivalency factor that's using a discount rate and interest or time to determine what to apply that, come up with that factor. And for each year of life, we do this calculation and come up with a total cost in each year. This table here represents that calculation, and you see in the column 6 there, I've got my depreciation expense discounted. Shows the formula there. There's some hidden columns that came behind this. Then I've got my cumulative operating and maintenance costs. I add those two together to get my total costs, and these costs are all discounted to current year costs. And then I have my equivalency factor there, which is basically a constant given an interest rate. And that equivalency factor is applied to those discounted costs to come up with your mean equivalent annual cost. Now, in this illustration, in year 4, my mean equivalent annual costs are $20,777, which is the least of the planning horizon that I have. So with this asset, I would want to replace it in the 4th year, because if I start to keep it beyond that 4-year horizon, my cost per year to own this asset is just increasing. If I were to keep it, nearly 10 years, I'd be looking at $23,000 a year over a $20,000 per year if I keep it 4 years. So I would have a significantly higher, almost $40,000 of costs over a 10-year life of that asset as opposed to a 4-year life. Now, common to this methodology is this is the life cycle graph, and this is pretty standard presentation of this calculation, where the blue line represents my capital cost, which is declining over time. The fuchsia pink line there represents my maintenance costs, which are increasing over time, and the burgundy sort of U-shaped line represents my life cycle cost, my equivalent annual costs. And you'll see in this example, years 4 to 5 or years 5 to 6 are probably my lowest costs. So somewhere in there would be the optimal time to replace it. Again, if I keep it out towards year 11 or year 12, I'm looking at $20,000 a year, whereas in year 5 or 6, I'm looking at $10,000 a year in operating and ownership costs. So I want to set my replacement cycles in between years 5 and 6. There's some challenges to doing these calculations, and as we've been developing the application, we've been doing some data analysis and running some models and looking at the data. And there's a couple things that, when it comes to putting this together, that make it difficult for fleet managers to do this on a regular basis. One is you got to have a good repository of data. You need a good maintenance system that has costs. Those costs can easily be identified and aggregated. But do you have enough history? And when we work sometimes with some of our newer customers that it might be new into our system, how do we handle it when they may only have 2 or 3 years worth of data in our maintenance system and some summarized costs? Can we use some sampling to do this? We've looked at that. And then there's outliers. Outliers are always a problem. What happens when the technician forgot to go home and log off the job, and rather than being an 8-hour job, it became a 70-hour job over the weekend, and we didn't go back in and clean that up, or someone fat-fingered 9999 into a meter reading, and all those things happen. Data can get corrupted, and then we may have some things that are just old and unique that had one-time big investments. So how do we handle those, and what are those influences? And then inflation, it's always something we have to deal with, particularly when we're going back and looking at historic data. How do we take old data and get it up into a constant number so that when I'm looking at first-year repairs of a vehicle that's 10 years old and the first year of repairs of a vehicle that's 1 year old, inflation is going to make those two amounts differ, but I want to be able to put those into a constant dollar. So part of the process is normalizing the data. And so over time, as we gather our data, we want to clean all that up. Data quality and capture is another issue, and as we've been working with some of our customers to implement, there's a couple of things that we look at, and one is just using job reasons appropriately. When I create a work order and I tag a job, am I being diligent about what type of work? And so can I easily identify what are included normal routine maintenance costs from non-target avoidable costs, things that really aren't part of the life cycle, but I have to maintain and I have to do. So is it easy to do that? Also, how people cost their labor is another factor too. If I'm using payroll rates and I'm paying technicians $15 to $30 an hour, that's going to look a lot different than someone who's using a fully burdened shop rate that might be $85 to $125 an hour. And my costs, I'm not capturing all my costs if I'm just using that payroll rate. And so I might be understating what those costs are, and it might suggest that maybe I keep things longer than I should. So we need some ability to handle, normalizing maintenance costs and looking at total value, total cost. What about warranty work? I mean, if I have a good warranty program, I should have a lot of avoided costs because the dealer or the manufacturer is paying for that for me. But if I do that work in-house, am I crediting that back, and how do I credit that back, and am I only getting partial payments? So how do we value that and capture that? And so these are all things that we've had to consider as we've built our model out and account for. Downtime, as I mentioned earlier, that can be another factor. How do I record downtime, and how does my system do it? Do I have everything set up to do that? Do I have shifts on assets so I capture non-work time from work time? Do I just look at total open to close time? How do I manage downtime? And then capital costs. Some people struggle with having complete capital cost histories in their fleet system. Maybe they've got it in a fixed asset system. And then another challenge is salvage. We don't all go out and sell a vehicle every year just to test the market to see what we can get for it. So we have to rely either on some external resources like a Blue Book or a Black Book, or some sampling or something, or just use a surrogate like depreciation to account for salvage history. True life cycle analysis would actually look at individual resale values in each year and factor that in. But most of us can't do that. So if I want to do this and I want to do good fleet management, how do I get all this information? Well, typically you get this from your fleet management system. It might not all be in the same place. You might have to go to maybe a fuel system or maybe a fixed asset system to get some of that information. But you run a series of reports, and you collect that data and you put it into spreadsheets, and you'd run a calculation, and you come up with this and build your models, and it's generally how most of us have had to approach this over time. Well, all of these requirements kind of led us to CAM, or Capital Asset Management, is the full name, but shorthand we call it CAM. This is a customer-driven initiative. Several years ago, during our users conference, I gave a presentation with the City of Calgary on life cycle costs. We presented a couple different methodologies and discussed that, and that drove a lot of discussion. We had a number of customers that came up to us afterwards and goes, I have a spreadsheet that does this. I do this regularly. This takes me forever to do. I have to get all this work, and everyone kind of came back and said, we really would like a tool to do this ourselves. And so as we talked with everybody, we put some requirements together. We said, life cycle costing is important, but we also need to use that and apply it, and the ability to build capital plans and manage the procurement and manage the disposal. Our fleet systems are great at managing operations and maintenance systems. We've had functionality to do these things over the years, but they haven't been, they're not our focus. So what we decided to do was take all these together and build an application, and that came up with the concept behind CAM. We really saw this as, at the center of everything is a data mart and an asset register that houses information that we extract from the maintenance system. What are our assets and what does it cost to own and operate those assets? All of that would be stored in this central repository. We want to be able to support the analysis, so being able to calculate that life cycle, but then use that data to help us manage plans and budgets, determine when to replace things and forecasting what those expenses might be. And then once that plan's approved, let's manage the procurement and let's track those assets through that procurement process and get them back into our maintenance system where they'll live until it's time to dispose of them, and then we manage the disposal. We've always intended that CAM was not to be just a module off of M5 or FA, so it would only be limited to one segment of our customer base. We wanted something that any AssetWorks customer, and for that matter, any fleet, could use. So CAM has been constructed as a standalone but yet integrated app module to our maintenance systems. You can install CAM on its own server. It does have its own schema, which can be independently installed, but is normally, if you're an M5 or FA customer, installed alongside it. We also wanted the ability to integrate in with ERP systems. We know many of you have to do your purchasing through Oracle or SAP, and so we've developed APIs so that we can link to those systems. So that's was generally the concept behind CAM, and what's evolved is really two modules or two sets of functionality. The first is really workflow-based. It's procurement and disposal. It's the process of requesting assets, going through and approving those requests, generating an order, tracking that asset through its production, the ability to order from multiple vendors of different components and have those components assembled and track that assembly, and then at the end get a final asset delivered and turned over into the fleet and entered into our maintenance system. And then at the back end, being able to have a similar workflow process to track the disposal. This is the functionality that we started our development on. We're actually getting ready. We're working on disposal now and should have that out either at the end of this quarter or first part of next year. So most of that functionality has been wrapped up. The second half of this really became more the data consumption, where the first part's producing data, it's generating transactions. The second half of CAM is really a consumption of that information. So, and this is where we analyze the information that we collect from the maintenance system. So coming out of M5 or FA or one of our competitive systems, really any maintenance system can provide us the information we need. We have this analysis capability, and this is what I'm going to talk about here for the remainder part of our presentation. But also, this will lead into the forecast and planning, and I'll talk a little bit at the end about where we're going with that and the ability, once I have that plan, to track and manage the budget, and that really leaps us back up to that request process. So this is what CAM looks like today after 3 years of development and a year of production. But key to all this is the idea of the data mart. So if you're an M5 or an FA customer, we have XML interfaces between the applications You launch them from those applications, and then they periodically send over transaction history into CAM. Again, CAM has its own set of tables for these. We don't read tables directly out of these other systems. We did this so that we can aggregate the data independently and also consistently, so that all the structures are the same inside of CAM, where an FA and an M5 work order don't quite look the same. They have basically the same information, but they're called things differently and put in different places. By consolidating everything into a single CAM schema, then we can utilize and use that data better. Now, if you aren't an AssetWorks customer and you would like to implement CAM, we do actually have batch interfaces that can be used to load that data using a template process, where you can extract it from your system, populate our templates, and then set those templates up to run on a monthly basis. We look for a file and we upload those into the system. This information doesn't need to be day-to-day, hour-to-hour. The way we consume it, we're really looking at period-by-period updates. We aren't that sensitive to a work order that was closed this morning, so this doesn't have to be run on a regular basis. You may want to run it a little bit more frequently if you have high volumes of records, just to cut down the processing time. But it's the kind of thing that, a once a month should suffice. A larger customer maybe wants to look at once a week. But those interfaces run and populate CAM. Inside of the CAM application, at the unit level, we aggregate all of this information. Now, we do take job and repair data over, task data, at that level, at the system assembly level, along with a reason code. So we do have a fair amount of granularity. What we don't bring over is we don't bring the technician that charged the time and the actual part that was issued, but we know how many hours were charged to that system assembly code on a given work order, and we know the number of parts, or the value of the parts and the value of the commercial work. We just don't know the real gory detail. But for what we need to do with it, that's sufficient. And in addition to maintenance, we bring over energy or fuel, trying to call things energy, just thinking about changing different fuel types. And then we also do bring over labor hours and downtime hours. And again, downtime just depends on the system. Both M5 and FA do accumulate downtime very similarly, with the idea between an open and completed work order, you can suspend the downtime, you can set up shifts on assets so that there's operating time and non-operating time. And so what we look at is the operating downtime and bringing that into the application. Now, one of the things we do is we do tag it with the month that it occurred in, but we also then organize it, though, based on the service month of the asset. So we group things by what occurred in the first month of the asset and what occurred in the 10th and 12th and so on. But we key it based on when it occurred, not in the life of the asset, as opposed to when it occurred on the calendar. It's a little bit different approach for how we store that data in our fleet applications, where it's typically stored on a calendar basis, not necessarily keyed based on the lifespan. But that helps us to organize it and do our capital analysis. Now, what I'm going to show you is our custom lifecycle cost module functionality. What this is a new application that we delivered this summer in our 15.2 release, I believe, that allows you to develop your own lifecycle cost analysis, where you can select which assets you want to include, you can modify parameters, and you can manage outliers and trends. And I'm going to walk you through how we do this. The thing is, each of these is unique, and you can actually make variations in scenarios of these. And this is different from a function I'm going to show you afterwards that we're talking about as a category trend, where we run a baseline based on default values of the category, and that's just run in the background to generate reference data. So the idea here is that I can build my own custom analysis and do my own models. So I'm going to get out of, if I can, get out of PowerPoint, and let's get into CAM. So I've already logged into CAM, and I've set up a couple different examples just so you don't have to watch it spin. Each model takes a couple, 30 seconds to a minute to run, depending on the size of the model. And how many records you include, and how far out you go. All those factors will determine into that. But I've pre-staged a few of these just so we can see. So I'll start first with the model information. When I set up a model, I can, sensitive here, I can give the model a name. And I can, when I save it, that'll save this data to that model. Now I can make it a private model or a public model. If it's a public, excuse me, if it's a public model, anybody else can pull this model up and view it. If it's a private model, it's restricted to my viewing only. I can change it, start it out as a private, play with it, and then once I'm done, save it and send it back as a public. I can, set some notes, just basically, create a header record for the model. The next step is determining what records do I want to use. Typically what we're looking at is a category, and a category is a grouping of assets that have the same form, function, application, 3/4 ton pickups, 3/4 ton pickups with 4x2s, police sedans, trash trucks. I might have a different category for a side loader and a rear loader. It just depends on how I organize my fleet and how I want to differentiate. Typically what we look at is different categories are created when the form or function changes, when costs between one type, one form, one function, one configuration is different, is significantly different. Maybe the application becomes different. It's a full-size sedan, but a full-size Crown Vic can be back in the day, could have been a taxi cab, a police sedan, an administrative sedan, maybe it's a building inspector sedan. Each of those had different lives because they had different applications, different usages, maybe different configurations of accessories. So generally we start with that category. We do have the ability, though, that within that you can look at different specifications. So if I wanted to compare different year, make, models of my sedans, I could. I have many thousands of different specifications over the years in this database of different types of sedans. Each one represented a different year, make, model. I could analyze one or two of those. I could also just come in and select, I want to see all my 2012s, use that data only. I can select a particular model range or make. I want to see all the Fords that belong within this category. So within the category, I do have the way to drill down. I also can look by department. So maybe I've got different regions or different users that maybe treat them differently, and I want to run this. I can do that as well. Locations, I want to run the beach versus the mountain fleet and see what the impacts there might be. So you do have the way to basically subdivide this data to look at different subsets. But again, the first task is, what am I going to do? So I'm going to work here with this CO10 again. So I type in, and this is just one of the features in CAM. I can generally type into a field, and it'll come back with data or with a list of values for me. Now, on the model parameters, I do have some default values set up on the category. So when I select that category, it does load those defaults in for me. Now, in this case, I'm going to include my warranty costs. So one of the options I have is whether or not I include or exclude warranty. I can also override my labor costs. So by default, what we do is we look at historic labor costs. We take data from 10 years ago, we inflate that to today's dollars and aggregate everything based on today's dollars. So we do apply inflation to that. But one of the things I could do when I set up my models, I could look and say, what happens if my labor rate's $125? What's that do to my life cycles? And maybe I just want to standardize everything. Maybe I'm using payroll rates and I had a blend. Some years I was on payroll and some years I'm on burden. This gives you a way to standardize that analysis. You can use a constant labor rate. What we do is we vary the hours based on when they occurred. So we have that, we apply it that way. I can look at downtime. Typically what I like to do is put a single dollar in just to see what the downtime records look like. If I leave it blank or zero, we just ignore it. But in the analysis, it may come down to, every hour that vehicle's out of service, it might cost me $100 or maybe $300 because I got a crew that's idle or I've got to go out and get a specialty vehicle. but I can put in a value for what that downtime might run. And then similarly, like we do with labor, we can also do a constant for fuel. We do take fuel, we apply some inflation factors to it to bring it into current year dollars, but fuel cost is so volatile. One of the ways I may want to standardize it is just put in a standard rate, $3 a gallon, $2 a gallon, and what happens when it goes to 6? Does that affect my life cycle? I could do those type of assumptions, again, looking at what we know is the quantity consumed and apply that cost. Then we have, for the capital, we look at depreciation. We have 3 different methods that you can apply: straight line, double declining, or sum of years. Straight line is, like it says, it's a constant amount year to year. Double declining, sum of years, use a formula. It's steeper in the first couple of years and flatter in the later years, and really tends to more represent how assets do depreciate on the market. But you can select the method that you like. And then we look at, what is that term that I normally depreciate for? How many periods do I spread that out over? And then we also have a salvage value, which gets built into that calculation. So I take the capital cost over 60 months with a 10% residual at the end, calculate a fixed rate per month, and apply that to come up with my straight line methodology. The maximum months to display says how far out do I want to go. I may have a 60-month life today, but I want to go out 8 years and see, what do those outer years look like. And then there's the discount factor that I apply. This is cost of money to your organization, typically 4 to 6% depending on the organization, but something you can find. We put that in there to, again, figure out to normalize things in current year dollars. I can also override the capital cost. I can normally what we do is we look at historic purchase prices, total capitalized cost, so what you purchased, what work orders you've capitalized and added to that, and we come up with what is sort of the average total cost in today's dollars, and we use that. If you want, you can go ahead and say, all right, well, it's going to, I'm going to use a $28,000 standard, and we'll work from that. And then we look at how do I track utilization for this asset? Is it based primarily on time or usage? Now, if I'm doing a backhoe, it might be time. Most sedans and pickups over the road vehicles, I'm going to have a distance odometer. So I set my parameters. The next step is how do you handle outliers? And so as I mentioned earlier, data can be dirty. There can be bad things out there. They can actually have an influence, and we may want a way to sort of exclude those type things. So we did some research and determined that a median absolute deviation for this type of data set is probably the best way to go. And what that does is it looks at what is the median value based on the distribution of all the values, determines the median, and then calculates a deviation from the median. Now, this is different from a standard deviation, which uses an average. The problem with the standard deviation is that it's really susceptible to a single outlier. The average of 0 to infinity is infinity. So with the median, if I do have a very high outlier, I'm not as susceptible to the average being skewed one way or the other, and it's a little bit better reliable statistic. So what we have is that you can determine how close do I want the data, how normal do I want the data to be in the model. I can be very poorly conservative and say, look, I want everything that's only 2 deviations from the median. So this is basically everything that's in about that middle 80%. We're going to exclude all the things at the low end, and then everything at the high end that's outside that tight 2 deviation range. I might want to be very conservative and say, look, I want to include everything that I can and just exclude the 1 or 2% on the tips that I don't want to factor in. You can apply each of these to the data at your based on how you feel and how you want, and you can come back and change these. By default, we leave everything at no. I'm going to leave all the maintenance there. I'm going to exclude conservative on the downtime. Leave my normal maintenance. Purchase, I'll find. I'm going to be get rid of some of the bad utilization records. And I just want to show you how those get applied when I run the model. The last piece is a trending function. One of the things we found as we started to build the model is that not everybody's got good data. It's got 15 to 20 years of data to go back. But maybe if you've implemented a system for 2 to 3 years, you've got vehicles that were 1 year old in that time frame. You've got vehicles that were, you know, 5 to 7. Some vehicles were 1 to 3. Just depends on when they were. So if we were to take all the 6-year-old data, or all the observations when in year 6, all the observations in year 7, that might occur in year 2 and 3 of the data, and then apply a trend to that. So it gives us a way to override and build out a method to aggregate data where data may not exist, or where good data, complete data sets won't happen. So if I say none, I'm going to get all the raw data, but I have the ability to come in and do either a linear or a quadratic, cubic, or quartic polynomial trend. And this is basically a second, third, or fourth degree trend, where what we look for is which of these trends has the best fit to the data. You'll see an option for best fit, and what that does is it runs every trend and determines the one with the highest R squared and applies it. Now, for most models, what typically I do is I start with the none, just because I want to see what the raw information looks like, and then come back and apply trends to see what happens. And again, the other thing that we're actually working on an enhancement where, because one of the things we found is that after the normal life of the fleet, if you've set your sedans to be an 8-year-old normal life, and you're trying to get rid of them after 8 years, but you know, because of budget reasons, sometimes you get some 9-year-olds, some 10-year-olds, and then you got underutilized vehicles. Those things that are in that afterlife phase, I might have observations in my data set for that. The problem is typically because they are lower utilized and the least cost, they tend to draw a negative curve in those outer years. And again, because I usually don't have as many of those individual observations, when I average them together, can actually skew everything down. So what we have is the ability that I can take this current life cycle here, 60 months, look at 60 months worth of data, the first 60 months, my normal lifespan for this category, trend on that data, and then use that trend to figure out those out years. You also have the ability to, whether you trend the actual data, trend the average, trend cumulative data. We put cumulative in so that if a customer just came on board and all we did was dump life-to-date data, we know what year that life-to-date data occurred, and then we can aggregate to that, and that gives us the ability to factor in those additional pieces. So I set all my things up, and I click the run, and it goes out to build models. Now this model will take me a couple seconds, a little longer than normal, because it's got about almost 1,000 records, assets that it's including in the analysis. But typically, it's within 30 seconds to a minute to generate. It usually doesn't take that long. Hopefully then the WebEx doesn't hold it up. So once the model returns, we get 4 tabs of results. The first one is a summary tab. It gives me, basically, I have my model name, tells me what my capital cost is, what my assumptions were in my capital analysis, or my capital parameters. I have 944 assets in this analysis. I have the depreciation calculation, using a straight line, basically an equal amount over time, out to 60 months, and then from there we just apply essentially a discount factor on those outer years. And then I have the aggregate maintenance cost. So I see what my maintenance was in year 1, 2, all the way out to year 8. So you see here the maintenance steadily increasing to year 4 and 5, and then tailing off in those outer years. Again, these assets are normally eliminated from the fleet around years 5, and so you see the impacts of those hanger-on units in bringing that average down. And then I see my downtime, and what I do see here is that I don't really have that much downtime in the back end, probably again because I'm eliminating assets rather than repairing them. That's another factor too, is that in those later years, if I did have a major repair, often I avoid that repair because I don't want to spend the money. And so how do I reflect that into that avoided cost in this analysis? And then I do have my cumulative cost. So that's the summary, that's the raw data. This is the calculation for the mean equivalent annual cost. So I've got my capital value, I've got my maintenance downtime and energy costs broken out. Now because I basically value downtime at $1, I have 356 hours of downtime on average in the first year, 545 hours on average in year 3. I sum up those operating costs. We do a cumulative sum of both the capital and operating costs to get my total discounted cost, and then I apply my equivalency factor that I showed in the earlier in the equation. And what this is saying is I ought to keep these things, because of the influence of these outer years, I could run them, 10 years. We know that's not necessarily the case, though, because this downward trend. And so, again, that enhancement that we're going to apply would actually be forecasting these years based on the trend of the first 5 years and ignore that outer piece, just to help us understand that relationship there and overcome those afterlife vehicles. They're like zombies in the fleet. And then, but what this is saying, though, in year 10 is that's my least cost. If I, kept the vehicles in, 3 years, I've spent about 17.5. If I kept it 4 years, I'm saving about $400 a year. And again, it declines almost $1,000 into year 5. So what we do is we highlight in green the year with the lowest, and then if it's within 5%, we highlight the remaining or any neighboring years within yellow. We can display this information graphically. I have here showing the capital costs over time, and you see that I'm going basically to 10% of my life cost in year 5 and then flattening it out. So that's one of the things that's influencing my curve. The other thing you do see is I have a decreasing maintenance in operating costs in these later years, again, holding on to some of those other vehicles. This line represents my utilization, so you can see my utilization is fairly steady from first year to second year on average, increasing out to about 112,000 after 8 years. And then this represents my life cycle cost curve. Now, like I said, I show you, the traditional theory has always been that this is a U-shaped curve. And in the analysis that we've been doing, what we're seeing, though, is these curves tend to be flat. So we have to kind of look at some additional data to help us understand what might be, going on and occurring, and helping us to set what might be the appropriate life cycle. So one of the things we did is we implemented a set of graphs that were brought to us by the City of Calgary. They've developed this methodology and used it and asked us to include it into CAM, and we agreed. And what we do here is, I'm going to remove a couple of these graphs just to simplify it, is we break the fleet into quartiles based on their utilization, their annual utilization. And so there's the lowest quartile. Those are the assets that have the lowest utilization per year. There's the highest quartile, the top 25% that have the most utilization per year. And then there's the middle 50. And what we've done for each of those is plotted what the maintenance cost is per year for each of those assets. And you'll see here that actually these low-use vehicles do have a peak, and this probably has to do with timing of the data. You see, have very little cost in year 1, but high in year 2. So we probably have a data timing issue we need to look at. But if we take that out and just compare, our median and our high, we'll actually see that the high-use vehicles do have a much higher maintenance cost, and then as compared to the median middle use and standard. So we might look at that, and we do see, things are going up and then dropping off, and then they are dropping off rather precipitously in the latter years. Now, in order to also help us look at the data, we've implemented scatter plots. And these scatter plots, what we do is we take the observations for each of the years, and then we plot those into the graphs as you show on here. So each basic dot represents an asset. and that asset's cost. And you see in the first year, we've got costs ranging anywhere from 0 to, what is that, almost $12,382. I've got a big jump in some assets out here that cost almost $22,000. Now these are $25,000 assets. I'm spending $22,000 in the second year to do some maintenance. On average, I'm spending about $4,500 in that second year. So down below, we show the total cost per year for each of those based on all the observations, what the average, the maximum, the minimum is. Minimum typically is usually 0. We have an asset that had no maintenance recorded. And then, what the median is, and then what the MAD deviations are. So one MAD deviation would be about 2,200 in the second year. So now when we also show the count, and you do see based on the count that how the number of observations drops in these later years, so I have fewer observations, so they become more statistically significant. Now we have also broken out this cost. Not only I can look at maintenance, I can look at my downtime distribution. And you see here downtime, now again, I applied an outlier removal. So what has been excluded from this analysis is any downtime units that are outside of whatever it was, 2 or 3 deviations, I forgot, that I applied. So it's fairly tight. I don't have many exceptions up above here. If I take that off and rerun this, you'll see that I've got units with a couple units with some very high downtime that were included in the data. Similarly, I didn't exclude any energy costs, so I have a few outliers up here. And then from a utilization standpoint, I did get rid of some of my outliers in the utilization to sort of normalize that distribution. So, just to give you some examples, here's a different type of asset. These represent some trash trucks. Again, these don't have any outlier applied, so you can see where I do have some exceptions in the data. I could go back now and decide that, based on this, that maybe I want to apply an outlier removal to that data. Let's get rid of some of the downtime and the maintenance exceptions. And then I can rerun my model and see what that influence has on the result set that I've generated. Now here I only looked at 7 years. Again, you can define how far out you want to go. If you've got trash or like aerial apparatuses, fire apparatus, might be a 12 to 15-year life. You can run the models for that long. You can go out 20 years if you'd like and see those impacts. We do, again, illustrate that. Again, I generated a curve specifically for this model. See, this does have very flat maintenance. Maintenance operating costs tend to peak up and then remain flat. When I have flat operating costs like this, my life cycle curve is going to decline because my capital costs are going to decline. Generally, one of the things we are seeing is that, because of better technology, speccing, maintenance process, we're not seeing this huge uptick in operating costs in later years. So, it's an interesting result. Sometimes you wonder what you ask for. Again, I can see the distribution of usage here. I have, again, probably some data things to look at on these low-use vehicles. The low-use vehicles may tend to have no use in certain times. And then I have my scatter plots, again, where here I applied my outliers to the maintenance and to downtime. So I have a lot of downtime occurring, almost a half a year of downtime for some assets in that first year. Now, this may be the way that we're upfitting the assets, and we're actually capturing some upfit work or prep work as non-capital maintenance work. So it might be included in some of this and capturing downtime around those events. So I've just about hit an hour. We scheduled this for that. I'd like to go ahead and open it up to questions.
Okay, everyone, we will open up the floor for some of your questions at this time. Just as a reminder, if you do have any questions, please be sure to send them to host using the WebEx chat tool on your screen. And provided that we do have enough time, I'll pass your question off to Mark, and I'll be happy to give you an answer. All right, Mark, first question. One of our attendees had asked if CAM is an access-based software program.
CAM is not. CAM is has an Oracle or SQL Server backend. Now, we do offer it as a hosted program, so if someone doesn't have that capability or everything, we can host it for them, and so they don't necessarily have to maintain the database. They just access it over the web.
Okay. Okay, our next question is in regards to step 3 that you had shown, Mark. It was the module parameters.
Mm-hmm.
And one of our attendees had asked which method has proven to be the most accurate model for resale value. How have you measured that accuracy, and is it possible to use actual disposition data instead?
Yeah, we haven't actually gone out and compared results yet on the method. Generally, the sum of years or the double declining tends to be the one that tends to probably the closest because it has a steeper drop in the first 2 years. We haven't opened up that table to plug it in currently. That is something we look at doing, where you could plug in resale values in each year, so you could model those as an input on the category. You could set what you expect that to do. It's not there now, but it's not something we can't do.
Okay. Another question, how do you compare apples to apples in total operating costs for assets at different ages when older units are driven less and maintenance is at a lower cost than at younger ages? If this is not corrected, wouldn't the life cycle ages be positively biased?
Well, it is true that as the older assets, and that's what I was trying to illustrate there with the scatter plots and with the data, is that if you do have older units in your fleet beyond the normal life, those units tend to be less utilized and less maintained. And so it does have a way, it does basically result in the trend curves to decline. And again, one of the things though we're missing is that in those older units, if I decide not to do some maintenance because they are old, and why would I want to put a $10,000 engine into it when I can buy it new? So there's a cost that's not shown there, that's not included. So yeah, it's one of the challenges that we faced when we started looking at the data. What is the impact of those? And so what we've done is we've implemented those tools so you can look at the range and look at your ability to include and exclude that information as you want and understand your fleet.
Okay. One of our other questions is in relation to some of the graphs that you demoed today, Mark. One of our attendees was curious to know what programming language they were generated with.
We use a tool called Sencha to do all of our, to develop CAM, and that's what CAM's doing, right?
Yeah,
okay.
Those graphs are built into Sencha, the JavaScript framework.
Yeah, Sencha is a JavaScript framework. I've got one of the developers here behind me.
Okay. This question goes a little bit back closer to the beginning of the presentation, and that is, how is ownership cost calculated? Is it based on original purchase cost, and do you then apply current purchase value and depreciation?
So we do it two ways in the life cycle model. One is a calculated method where we take each asset's original purchase price and other capital journal transactions that we may have. So if you have capital adjustments, you've done capitalized work orders inside of the FleetFocus application, we attribute those to, we add those to the value. So we come up with a value for each asset based on its total capitalized value. And then we do restate that in current year dollars. So if you bought that asset 10 years ago for $20,000, it might be $24,000 today. So there's that method where we use that calculated value and come up with the average. Or there is the plug and play where you go with the assumption of what you're paying for that asset today, and apply that current cost to the model. So essentially, you're putting in historic maintenance costs to get the trend for that type of asset, and then you're applying the current capital cost on top of it. Another thing that we found, too, is looking at some of this data is the capital costs are not keeping up with the inflation of, or maintenance costs are not keeping up with the inflation of capital. And so high capital dollars sometimes suppress that equivalent annual cost.
Okay. Also earlier in the presentation, you talked a little bit about having adequate sample sizes for calculating life cycles. Mark, you had mentioned, having enough assets or a large enough sample size to do that. In your experience, do you have a rough estimate as to what would constitute enough assets for doing so?
Well, statistically, they say good samples should be somewhere between 25 and 30 to do, effective statistical. And actually, our trend, the trending tool that we do have does have a minimum number of records needed in order to calculate a trend. It's in that range. Now, without the trend, though, you can still plot a 5-unit category. You got to be careful. One of those could have been a real dog and just skew the whole thing. So, the more observations, the more, averaged things are. So it's just, one of the considerations anytime you're dealing with data sets. We don't, other than you can't run the trends on small data sets, you still can run a model in AM with, few units.
Okay. Okay, another attendee had asked how you account for a specialty unit's life cycle. Examples would be a fire truck or a special pumper. Yeah,
so those fall in those small sample set things there. And what we're looking at, you may not be able to run a statistically reliable model for those small sample sets. But we can still calculate, for that group or for that asset what its cost trend is over time. And that's where we look at things like cost per mile, cost per utilization, and presenting some of that information and using that then to make the determination. And that's also, the idea I mentioned early on about, part of the process is there's a rational decision-making process where you take factors like safety and obsolescence in technology and you weight those, and then one of those factors then becomes cost and cost over time. That might be why you go and say when you replace things.
Okay. Mark, our next question comes from one of our customers who wants to know which M5 table cost data is pulled from.
It's pulled from OJOB. So the maintenance data comes from OJOB because we get it at the system assembly level. So we're actually pulling it at the job detail. Downtime comes from unit downtime, and one of the fuel views supplies the fuel data. And capital data comes off the capital journal.
Okay. Yeah, we do just have a couple more questions. Going to do my best to get to these, and then unfortunately, it looks like we have run out of time. But Mark, can you talk a little bit about what the capital depreciation formula looks like?
Yeah, I mean, I don't know if I have time to do that given our time frame. But there's, the straight line depreciation formula is purchase price minus salvage divided by the number of periods. That one's fairly straightforward. The sum of years and the other ones I don't have, I can't spout those off, but we can make those available if they want to email me. I can give them the formulas. You see my email address there. Feel free to email me if you have questions. You can also find me on LinkedIn. You want to join me out there, or you can tweet me at Twitter. I'm happy to respond to you.
Okay. All right. Our last question. After life cost calculation, this attendee states that they can get the lowest mean equivalent annual cost year. But how do they prioritize the equipment that have already exceeded the lowest mean equivalent annual cost year?
Well, actually, that's some functionality that we're going to be working on next year. It's a prioritization process. Now, this is similar to already what's in M5 and FA on the replacement analysis. And that's a scoring algorithm where, based on the asset's actual experience relative to the category's standard or mean, we score each asset. So we're going to be implementing that into CAM. For those of you that do get the PowerPoint or the summary presentation at the end of this, we will be emailing that out. There are about a half dozen slides I didn't have time to go into today that talk about some other future applications in CAM. That includes category models, so basically using category defaults and calculating those in batch. And then also some replacement and forecasting functionality that we'll be doing. So you may want to take a look at those. But included in that planning capability, probably later next year, is going to be CAM's version of that replacement scoring, so that you can prioritize assets, you can score them, and look at valuing assets. And you have the ability to look at things like what might be the upcoming maintenance cost, age, utilization, expected fuel consumption, things like that, that you can actually evaluate and score on. So that is actually also one of the tools for lifecycle. Is you could, and you'll see some examples in that presentation, the PDF, of where we are going to be plotting out an asset relative to the category and plotting out each individual asset's cost, so you can compare an asset to other assets and to the category and help in that decision making and determining which one has the best cost. Maybe the one with the higher cost might be the one you want to replace.
Okay, great stuff, Mark. Unfortunately, everyone, it does look like that's all the time we have for today. At this time, I would like to thank you all again for taking the time to attend today's presentation, and hopefully all of you have secured some valuable takeaways to keep in mind moving forward. Mark, I'd like to thank you on behalf of VastaWorks once again for sharing your expertise and product highlights with everyone today. And as you can see, Mark's contact information is available right on this slide should any of you have any follow-up questions or concerns. As Mark had also mentioned, we will be sending the link to this webinar recording as well as the PDF version of the presentation out to all who registered, and also customers can find all webinar recordings on the VastaWorks community. All right, thank you all for attending today. Have a great day. We look forward to having you with us next time.
Thank you.